Math 2414, improper integrals, infinite limits of integration, example 3. Yeah, business is about to pick up. If you've seen the previous two videos, and hopefully you have, they didn't take too terribly long because the antiderivatives were easy to calculate once we set up the proper integral, and then the limits weren't too bad either. Determine if the integral from negative infinity to 0 of x e to the x dx converges or diverges. If it converges, find its value. Now would be a good time to remind those of you who are in my class that prior to these videos were a lot of videos about how to integrate things, different integration techniques. Integration by parts, trig integrals, trig substitutions, partial fractions. Those are still options, and we're going to use one of those options here. All right, so what's our first move? Well, the first move is to replace the infinite limit of integration with a variable. So we'll replace the negative infinity with the t. And by the way, you can use any variable that you want besides the one already in play, so don't use x again. So let's find the definite integral from t to 0 of x times e to the x dx. And it might help to find the indefinite integral first, or just drag along the limits of integration. Now, we are going to use integration by parts here. Just a quick reminder about what about this integrand says to try it. In the phrase integration by parts, parts refers to parts of multiplication problems, aka factors. This integrand is composed of three factors, x, e to the x, and dx. And when you do integration by parts, you're looking for a part that's easy to integrate and another part that will vanish upon differentiation, with enough differentiations. But we've run across this integral before, so what's about to happen shouldn't be anything new. Let's let u equal to x and dv equal to e to the x dx. Remember, when you do integration by parts, you split the integrand into a u and a dv. Then you differentiate the u to find du, but the derivative of x is 1, so du is equal to dx. And then you integrate the dv to get v. Well, the integral of e to the x is e to the x. And then we use the setup for integration by parts. Remember, integration by parts doesn't do an integral, it just changes it to a different integral. The setup for integration by parts, just as a reminder, the integral of u dv is equal to uv minus the integral of v du. And we have all those pieces. U times v is x times e to the x, and that's getting evaluated from t to 0, minus the integral of v du. The integral of v, e to the x, du, which is dx. This is from t to 0. Well, this is an easy one to evaluate. We have x e to the x minus e to the x, and all of this collectively is from t to 0. So let's substitute the upper limit and lower limit. When we put in 0, we get 0 times e to the 0, which is 0, minus e to the 0, which is 1, minus, when we substitute the t for all the x's, we get t e to the t minus e to the t. And there's not really any terms we can combine, but we can get rid of the 0, distribute this negative, and maybe put things in a cleaner order. For example, I'm going to save the minus 1 for last, and when I distribute this, this will be negative, this will be positive. Let's put the positive piece first, e to the t, and let's put this minus t e to the t after it. That's just my preference. You could have written negative t e to the t plus e to the t minus 1, or any of the 6 permutations of juggling those things around. All right, so there's our antiderivative. We have the answer to the first question. We're nowhere near out of the woods yet because our next move is to take the limit as t approaches negative infinity, and we'll analyze it one piece at a time. So let's summarize this to the side just so we can clear this off. The integral from t to 0 of e to the x, x e to the x dx was equal to e to the t minus t e to the t minus 1. All right, so there was our first move. Our second move is to now take the limit of that expression as t approaches negative infinity. Because remember, the t was replacing the negative infinity. So second, we need to take the limit as t approaches negative infinity of e to the t minus t e to the t minus 1. Now, as long as things are continuous and exist, you can split this up into 3 separate limits. Limit, limit, limit. Now, how do we know if we can split it if we don't know if it exists yet? Good question. Assume it does exist and hope nothing goes bad. So let's split this into 3 separate limits. Limit as t approaches negative infinity of e to the t minus the limit as t approaches negative infinity of t e to the t minus the limit as t approaches negative infinity of 1. 2 of these 3 limits are easy. The easiest one is the last one. This one is independent of the value of t, so it doesn't matter what t does, this limit is 1, so we're okay there. What about the first one? Well, this is one of the limits that we reviewed in video 3, I believe it was. It was 2 or 3. It was video 3. Without rehashing everything that happened there, the graph of e to the x looks like this. And so when x approached negative infinity, as x approached negative infinity, e to the negative x approached 0. Well, the fact that I'm calling this t instead of x is completely irrelevant. I could call this the t-axis instead of the x-axis. But no matter how you slice it, this limit is 0. So now the only one we have to figure out is the one in the middle. So let's pull that to the side for a second. Limit as t approaches negative infinity of t times e to the t. And on the first glance, you might think this is infinite. But let's think about this for a second. The t by itself is approaching negative infinity. And maybe I should put a quote around this equal sign, because I'm about to bend the notation just a little bit. But if we were to do basic limit strategy, which is plug in the values and hope nothing goes bad, and then bent it even further by trying to plug in negative infinity, the t would become negative infinity times e to the negative infinity. And again, I'm breaking all kinds of notation rules here. We're just kind of thinking out loud. But isn't this just 0 like it was here? Oh no, we're battling something approaching infinitely large in the negative direction times something approaching 0. So who's going to win that battle? L'Hopital's rule is coming in. This was an example of what was called an indeterminate form. Again, I'm kind of abusing the notation, but loosely speaking, infinity times 0 is indeterminate when it's the answer to a limit. That simply means that we haven't determined the limit yet. It could still be anything. But we can't use L'Hopital's rule because L'Hopital's rule is only good for certain indeterminate forms. Just a reminder, I can find a place to put it. L'Hopital's rule, and I'm just going to give you the skimpy version of it. I'm not going to fill in all the gory details. It says something like this. If the limit as x approaches some number, we'll call it a, of f of x over g of x equals, and again I'm abusing the equal sign here, infinity over infinity or 0 over 0, then the limit as x approaches that number, and that number can be infinity by the way, of the ratio of those two functions is equal to the limit as x approaches that number of the ratio of the derivatives. Take the derivative of the top, take the derivative of the bottom, if they exist. In other words, if both limits exist, then they're going to be equal to each other. So if we can get infinity over infinity or 0 over 0, then we can take the derivative of both sides and try the limit again. But this is a product, not a ratio. So how do you turn a product into a ratio? The answer is write it as one number times the reciprocal, or divided by the reciprocal of the other. So in other words, here's the trick. We're going to take t times e to the t and rewrite it as a ratio, which means somebody has to move from the top to the bottom. I nominate the e, because if I want to move something with an exponent from the top of a fraction to the bottom, I simply have to put a negative on its exponent. So let's try this limit, which is equal to this one, just a little bit of algebraic smoke and mirrors. And let's see what happens if we quote-unquote plug in infinity. Excuse me, not infinity, negative infinity. Well, the top is negative infinity, but the bottom becomes e to the negative infinity, which is e to the infinity. And again, I'm really abusing notation here. E to the infinity is infinity. This is not only indeterminate, but this is a setup where we can use L'Hopital's rule, which from this point forward, I'll just abbreviate with capital L apostrophe capital H. Now that we've got the correct indeterminate form to use L'Hopital's rule, we can try the limit again by taking the derivative of both sides. So, limit as t approaches negative infinity, but now differentiate each side with respect to t. The derivative of t with respect to t is 1. The derivative of e to the negative t is e to the negative t, but then the chain rule says times the derivative of negative t, which is negative 1. So let's see what this does. This gives us 1 over, well, I've already broken the notation so much I might as well keep doing it. I hate saying this, if I plug negative infinity here, I get e to the negative infinity, which is e to the infinity. Well, that's 1 over negative infinity, because e grows without bound. Well, that's equal to 0. And again, I'm so, I fear that some mathematician's going to watch this and go, oh my gosh, you can't say any of those things, and I know what you mean. But for the purposes of getting through this limit, we're going to break the notation for a little bit and plug in some infinities and then do some infinite arithmetic. Namely, 1 divided by infinity is 0. All right, so what does that mean? Well, that means that the answer to this limit is 0, which means this limit is 0, which means this limit is 0, which means this limit is 0. And so we ended up with, oh my gosh, oh, I can kick myself. I can so kick myself. Wait. Never mind, sorry. I was sitting here thinking, this limit's 1. No, it's not. That's what happens when you've been making videos and you're hungry. All right, so let's see what we're left with. 0 minus 1. So it looks like our final value for the limit is negative 1. That's the answer I meant to get. I borrowed this from one of the problems in the book that I'm using. So if you'll indulge me just for a second, I'll log back into my computer real quick. And we'll just make sure that I didn't make some silly mistake. And I know what some of you are thinking. Don't you know the answers to the problems before you do them in the videos? And the answer is, well, not always. Because I just set it up and do it. And I don't mind improvising the problems, because when I make mistakes, which I've made before, it points out that you're human, but mistakes are good things to learn from. So let's just check out this example that I stole from the book. And yeah, they got negative 1. I was a little taken aback by the fact that the answer was negative, but upon further inspection, of course it was going to be negative. Think about the graph of this thing. We're going from negative infinity to infinity, negative infinity to 0. This is always negative over here. That's always positive. Negative times positive is negative. The graph of this thing is below the x-axis, so when we calculate the area, it's a negative area being below the x-axis. All right, I hope that one didn't discourage you too much, but hey, some of these problems are going to get like that.